Chapter 19, Organic Chemistry, Saturated Hydrocarbons. What is organic chemistry? Well, organic chemistry is the chemistry of carbon. Carbon-based molecules are organic molecules. And so organic chemistry is the chemistry of carbon. This involves naturally occurring chemicals and also synthetic chemicals, which have been synthesized in the chem lab. And here, the picture at the beginning of the chapter and on this PowerPoint, this is a carbon nanotube. And this is carbon-based, so it is organic chemistry. With the history, there used to be a vital force theory, and the basis of this theory was that organic molecules could only be produced by living things because they had the vital force, the life force. However, Wohler in 1828 synthesized urea from scratch using cyanic acid and ammonia. And this was the very beginnings of organic chemistry, because this was proof of concept. He said, no, you don't need a living thing to produce organic molecules. I synthesized urea from scratch. And because he did that, chemists wondered, well, what else could be synthesized? And pretty soon, millions of molecules had been synthesized. There is no theoretical limit on the number of possible organic compounds. And so there could be trillions of compounds synthesized in the next 100 years. The greater the number of carbon atoms, the higher the flexibility of arrangement of the atoms. So carbon is unique, and it's the only element that's able to bind to itself hundreds of times in a row and still be completely stable. And this is why life is carbon-based, because carbon is the only atom on the periodic table which has the properties necessary to make the gigantic biological molecules necessary for life. Example of organic materials. We have nutrients, fuels, fabrics, wood and paper products, paints, varnishes, plastic, dyes, soaps, detergents, cosmetics, medicines. Most chemistry that you see on a day-to-day basis is organic chemistry. So which one of these is an organic compound? Well, we remember, organic chemistry is the chemistry of carbon. And only C, propane, contains carbon. So that is the only organic chemical up there. The carbon atom, atomic number 6 protons, 4 valence electrons. Its electronic structure was 1s2, 2s2, 2p2. And here we have a Lewis dot structure for carbon. Organic compounds are saturated if all the bonds are single bonds. They are unsaturated if there are double bonds. For example, this double bond right here. Ethylene has a double bond. That is unsaturation. So if all the bonds are single bonds, just one line representing 2 electrons binding all the atoms together, you have a completely saturated organic compound. If you have double or triple bonds, you have an unsaturated organic compound. Bonding and shape. Vesper states that electron pairs repel each other, and that explains the shape of these organic molecules. You might be thinking that the furthest 4 atoms can get away from each other is 90 degrees, but that's in 2 dimensions. If you use all 3 dimensions for a tetrahedral structure, the atoms can get 109.5 degrees away from each other, leading to our common tetrahedral shape. If there's a double bond, now we only have 3 electronic groups in Vesper theory coming off the central carbon, and so the bond angle will be about 120 degrees. And in the case of a triple bond, we only have 2 electronic groups coming off that central carbon per Vesper theory, and so the furthest away they can get is 180 degrees. And so we'll see these 3 degrees a lot in organic chemistry. 109.5 degrees, 120 degrees, and 180 degrees. So, estimate the bond angles around carbon 1 and carbon 2. Well, we look over here. Carbon 1 has 3 electronic groups coming off of it. A single bond, and a double bond. And the furthest away 3 electronic groups will get in space. And again, because of Vesper theory from Chemistry 1, electrons are all negatively charged. Negative charges repel other negative charges, and so they try to get as far away from each other as possible and get maximum spreading out. For carbon 2, you have 4 electronic groups coming off that carbon, so that everything will be 109.5 degrees away, giving us our answer of D. 120 degrees around carbon 1, 109.5 degrees around carbon 2. All right, illustrations of organic molecules. Here is a structural formula. It's a line structure. Here's a molecular model, and you have a ball and stick model with different shaped balls representing the different elements. Here we see a Lewis dot structure, a complete structural formula, a condensed structural formula, a line structure, and in the line each dash is a CH2. So that this point is a CH3. This bend here is a CH2. And this point here is a CH3. And this is just a really fast way to draw organic chemicals. If you have any atom besides carbon or hydrogen, they have to actually be stated. And so if we had, for example, rubbing alcohol, you'd have CH3, but here you would have to show the OH. And the hydrogens are just understood. So at this point, because carbon will bind to 4 things if there's no double or triple bonds. Since there's one carbon-carbon bond here, you have 3 understood carbon-hydrogen bonds, 3 understood carbon-hydrogen bonds, and then there's a hydrogen here that, again, is just understood to be there. And so basically it's a super shorthand way to draw organic molecules where you just fill in a hydrogen everywhere that there's a spot to attach anything to carbon. Here we have a ball and stick model. Here we have a space filling model. So these are 6 different ways to draw the molecule propane. And this is an example of how to take a condensed structural formula into a line structure. Again, CH3 is here at 1. That point is a CH3. And then 2, 3, 4, 5, and 6 are all CH2s. And you end at 7. Again, a CH3. And again, there's 4 things always attached to a carbon. So here, it's just understood that there's 2 hydrogens. And that's true for all of these atoms. And so it's a very fast way to draw organic structures. You're just drawing the carbon backbone and any non-carbon hydrogen atoms, and then it's just understood that the hydrogens are filled in as would make sense. Remembering that there's always 4 bonds to a carbon. I can either have 4 single bonds, 2 single bonds and a double bond, 2 double bonds, or a single bond and a triple bond, but there's always 4 bonds on a carbon. So, write the structural formula and the line structure for propane. Well, here's the structural formula, CH3, CH2, CH3. And then our line structure, CH3, because there's only one line coming off carbon. So there's one carbon-carbon bond, which we see right here. So in the line structure, it's just understood that there are 3 carbon-hydrogen bonds, which correspond to these 3. And they're not written, so that's why it's kind of confusing at first, but once you get the knack of it, it's a really fast way to write the molecules. Organic compounds are classified based on the functional groups they contain. And functional groups are all the atoms that are not carbon or hydrogen. So we have alcohols, that's an OH is there. Aldehydes, you have R dash, and it looks just like that. R is like X in algebra. It's just a variable that means any organic molecule. And for an aldehyde, you have a terminal ketone group. So that is an aldehyde. What makes it an aldehyde is that there's a hydrogen here. If there was carbons on both sides of your carbonyl group, you'd have a ketone, like acetone. So here is a picture of acetone. So the only difference between aldehydes and ketones are aldehydes have a hydrogen at the end, whereas a ketone has carbon on both sides of the carbonyl compound. Carboxylic acids have a COOH group. And here we have the acid group. Esters. This is from the condensation of an acetic acid and an alcohol. We have our R group. Then you have a carbon, there's a double bond oxygen, and then there's another single bond to oxygen. and that is an ester. In a amine group, you have nitrogen coming off, and in an amide, you have that carboxyl group and then a nitrogen. So these are the basic functional groups which we'll cover in organic chemistry. So identify the functional groups of the following compound. Alcohols. Do we see any alcohols? No. Aldehydes. Do we see any aldehydes? Also no. Ketones. Do we see any ketones? No. This double bond O is not a ketone, because to be a ketone, it would need a carbon here, which it has, but this atom couldn't be an oxygen. That'd have to be a carbon. Because that's an O group with another R group, that's an ester actually. Here, because of the amino group coming off of it, that's an amide. And here, because the OH group, the acid moiety, this is a carboxylic acid. So we have a carboxylic acid, an amide, an ester, and then an amino group, just an NH2 by its own right here. These are the different functional groups that are there. Hydrocarbons are organic compounds that contain only carbon and hydrogen, nothing but carbon and hydrogen. So example, hot paraffin wax. And it's not really a wax, it's just a hydrocarbon. Waxes are extremely big esters, but there is the oxygen atoms in a wax. Whereas paraffin is just a really, really, really pure big hydrocarbon. So it's just carbons and hydrogens. Aliphatic is what we've looked at so far, open chain carbons. Aromatic groups have benzene rings, and that we will cover later. And if there's only single bonds, we have an alkane. If there's a double bond, we have an alkene. And if there's a triple bond, we have an alkyne. And if there's a single or double bond and it's circular, you have a cycloalkane or a cycloalkene. For example, cyclohexane. Looks like that. Or cyclohexene looks like that. Hydrocarbons are the principal source of fossil fuels. So natural gas is like methane, ethane, butane, propane. Petroleum, gasoline, kerosene, coal are mostly hydrocarbons. And fossil fuels are a primary source of heat and fuel. And fossil fuels are organic chemicals because fossil fuels used to be plants. They were ferns 60, 70 million years ago. Those plants absorbed carbon dioxide using solar energy from the sun and photosynthesis, fixed it into organic molecules, and then they got buried, and over time, the organic molecules transformed into what we know as fossil fuels today. And so they are organic compounds. And when you burn them, you get carbon dioxide back. Alkanes, again, are saturated. They are straight chain. They can be branched, meaning here we have a branched. Straight chain is completely linear. So just in a single file line. It can be branched. Things can branch off, definitely. But to be an alkane, only single bonds, completely saturated. And the general formula is CnH2n plus 2. So for propane, C3H8. Because C3H, 2 times 3 is 6 plus 2 is 8. Butane, that would be C4H10. Because 4 times 2 plus 2 is 10. So this is the general formula for open chain alkanes. And here we see methane, ethane, we see propane, butane, pentane, hexane, heptane, octane, nonane, decane. And in every case, the formula is the number for carbon times 2. So 1 times 2 is 2 plus 2 is 4, CH4. 2 times 2 is 2 plus 2 is 6, C2H6. 3 times 2 plus 2 is 8, C3H8. 4 times 2 plus 2 is 10, C4H10. 5 times 2 plus 2 is 12, C5H12, and that is true for the rest of them. And notice as the molecules get bigger, their boiling points slowly increase, their melting points slowly increase. And so basically hydrocarbons go from gases, like the natural gases, methane through butane, And then you have your extremely thin liquids like pentane, hexane, heptane, octane. And you have your thicker liquids like engine oil. And then it gets even thicker and you have semi-solids like tar. And then it gets even thicker and we end up with asphalt. All of those things are petroleum products. And as the molecules get bigger, there's more van der Waals forces between them. So you have more intermolecular forces, and it slowly goes from gas to liquid to viscous liquid, like syrupy liquid, to semi-solid to thick solid. So what is the formula for an alkane with 16 carbons? Well, 16 times 2 is 32 plus 2, 34. C16, H34. Because it's 16 times 2 plus 2 gives us 34 hydrogens. Write the structural formula and the line structure for the straight chain alkane that has 8 carbon atoms. We have the structural formula, and then we draw a line structure. The carbon atom. Carbon has the ability to form 4 sigma bonds because of its ability to hybridize. This is a kind of a difficult topic, but basically the electronic orbitals are hybridizing. So imagine taking one s orbital and 3 p orbitals and throwing them into a blender and blending them up, and we get 4 sp3 orbitals. Notice it was 1 s orbital and 3 p orbitals. So this concoction is 1/4 s, 3/4 p, thus sp3. And the 1 is understood. So 1 part s, 3 parts p, and all 4 of the orbitals are the same. So it's like blending blueberries and strawberries. You put them together and you blend it up and you get a homogeneous mixture. They started as 2 different things. So over here we see 2 different things. But when we're done, they're all blended up and they're all the same. 3D bonding in alkanes. Because they're all single bonds, there are 4 single bonds coming off of each carbon. So they're sp3 hybridized. And they form a tetrahedral structure. Alkanes form tetrahedral structures. Isomers. These are molecules that have the same molecular formula but different structural formulas. So butane, there's 2 different ways to draw C4H10. We can have the 4 carbons in a row, or you can have one branched off. And so these are isomers. With methane, ethane, and propane, there's only one way to draw those molecules. But when we get to butane, there's 2 ways. And so it became butane and isobutane. With pentane, there's 3 ways. So let's draw them. One is going to be a complete straight chain across. One will have 4 across and 1 branches off. And one we'll have 3 across and we have 2 branches. And so they were named pentane, isopentane, and neopentane. But chemists soon realized that as the molecules got bigger, they could have more and more and more isomers. And so this system of having little nicknames didn't work. And we needed a system for naming that could be used for lots and lots and lots of isomers. So, naming alkyl groups. Alkyl groups have 1 hydrogen less than the respective alkane. The general formula for alkyl groups is CnH2n plus 1. Because it's an alkyl group because it's attaching onto something. So it's a hydrocarbon group that's attaching to a bigger group. So methane becomes methyl. Meth means 1 in organic chemistry. Eth means 2. Prop means 3, but means 4. And those are the different prefixes. In intro chemistry 1 we talked about mono, di, tri, and tetra. 5 it goes penta in both. But organic chemistry has 4 unique prefixes. Instead of mono for 1, it's meth. Instead of di for 2, it's eth, E-T-H. Instead of tri for 3, it's prop. And instead of tetra for 4, it's butyl. So here we see methyl group, ethyl group, propyl group, butyl group. And then, as you'd expect, it goes back to penta. Remember pentane, penta for 5, hexa for 6, hepta for 7, octa for 8, like an octopus, nona for 9, deca for 10. So it's just the first 4 prefixes in organic chemistry that are different than what we've seen before. In other groups, Isopropyl. It's a propyl group, but you're connecting at the middle, not the end carbons. Isobutyl. This is a group where you connect, the 3 carbons are in a row and one's branching off, but it's branching off the middle. In sec-butyl, the carbon's branching off the first carbon. And in T-butyl, it's branching off the middle one here. So, a primary carbon is a carbon that's only attached to one other carbon. So it's typically terminal carbon, like if we have ethanol. This last carbon is primary. It's only attached to one other carbon. Secondary would be like rubbing alcohol, isopropanol. This carbon is attached to 2 carbons. So this carbon has a carbon on one side, and it has a carbon on the other. Since it's attached to 2 other carbons, it's a secondary carbon. And a tertiary carbon is attached to 3 other carbons, like T-butyl alcohol. And then each of them have 3 hydrogens there. So that is a tertiary carbon, because that carbon is attached to 1, 2, 3 other carbons. And it's not covered there, but a quaternary carbon would be attached to 4 other carbons. So if all 4 bonds were to other carbons, it's a quaternary carbon.